Okay, next we're going to talk about oscillators and clocks. So an oscillator on a microcontroller generates a periodic signal, so like a square wave, like that. Okay, so it's basically a circuit that generates that signal. A clock, on the other hand, is derived from the oscillator and it provides the actual timing signals used by the microcontroller's CPU and peripherals for synchronization. So our particular PIC has, or microcontroller, has what's called a fast resistor capacitor, or FRC oscillator on board. And it uses a resistor capacitor circuit to generate a stable clock signal without requiring some external crystal or resonator. You can actually use an external crystal or resonator to give a very precise clock signal. Unfortunately, the FRC is not very accurate. Um, so off the top of my head, I think it's like your timing will be within maybe 1 to 5% of what you um, think it should be. So generally, for very precise timing, you use a crystal, but um, for our use, this is perfectly accurate enough. And FRC oscillators are typically used for like cost-effective applications or a fallback if an external oscillator fails. So basically the trade-off is it's faster to start up and it's cheaper, but it's less accurate compared to other crystals or crystal oscillators. All right. So of course, most robot applications, I would say all robot applications, need precise timing to do what they need to do. So let's take a look at this little video here. Um, so here's some robots, some funky music, packaging Slim Jims or some Slim Jim shaped object. And let's see, so you've got these robots that are precisely timed with the conveyor. And of course you need oscillators to do that precise timing so everything's coordinated. All right, let's shut that down. Okay. There we go. Okay, so let's talk a little more about the math behind oscillators and clocks. So microcontrollers, our microcontroller has an oscillator, and it will generate pulses at a frequency of what we call FOSCs, the frequency of the oscillator. So the period of the oscillator is 1 over that oscillator frequency. Clock instructions, on the other hand, are how fast each individual assembly line of instruction is executed. So for each clock instruction clock cycle, there's one assembly line of code that's executed, and the frequency of that clock instruction, we'll call it FCY, is half the oscillator frequency. Okay, so if the frequency is half, then of course the period is twice the oscillation period. So much larger time, well, twice the time for each clock instruction. So our PIC has an 8 megahertz oscillator. So our oscillator frequency is 8 megahertz. And our period then is 1.25 times 10 to the negative 7 seconds. Okay, so how fast do instructions execute? Well, we've got an 8 megahertz oscillator. We divide that by 2. That gives us a clock instruction rate of 4 megahertz. And that corresponds to a clock instruction period of 0.25 microseconds. Okay, so that's, just to reiterate, that's always the case. The fastest we can execute instructions would be 0.25 microseconds, okay? And that's based on a oscillator speed of 8 megahertz and a clock speed of an oscillator frequency of 8 megahertz and a clock frequency of half that at 4 megahertz. Okay, so we've got lots of oscillator options. However, we can set the oscillator speed on the PIC to various values. So we can operate at 8 megahertz, but maybe you don't want to use up all that power. Maybe your application it isn't so precise, and you don't need such precise timing, so you can use something all the way down to a 500 kilohertz oscillator with a postscaler, which then slows it down by some factor even more. So the default oscillator speed on our PIC is 8 megahertz, and we call that the fast resistor capacitor div oscillator. So the FRC div is the default, and the div gives you a divide by 2 postscaler. So what that means is you have an 8 megahertz frequency for the oscillator. You divide that by 2, so then you have 4 megahertz oscillator, and you execute instructions at half the frequency of your oscillator. So you execute instructions at 2 megahertz. So this is the clock frequency, and this is the oscillator frequency after the divide by 2 postscaler. We'll talk more about postscalers in 1 second. But basically the take-home message is we can set up our PIC to operate at different clock speeds and different oscillation speeds. And the reason you may want to not use the 8 megahertz, or the reason you may want to use the 8 megahertz is maybe you need to execute instructions at that speed. Maybe you don't. Also, if you will be using timing and counters and timers and counters in your application, and those things increment at some as a function of the clock speed, and so maybe you don't want to fill up those variables so quickly if you don't need the precise timing, so you might want to use a slower clock for that reason. And power is probably the biggest one. Using fewer clock cycles consumes less power. All right, so how do you select the oscillator speed that you want for your application? Well, so the oscillator speed can only be set prior to runtime using this preprocessor directive. Okay, so anyway, using this hashtag pragmaconfig line of code, this writes to these certain bits, the FNOSC bits of the FOSC SEL register, and basically that sets the oscillator speed. So that has to be, this line of code has to be typed in outside of your main function. So let's just take a look at that register. So let's take a look at the FOSC SEL register, and we'll go here. So how I usually find these is I just type in the search bar FOSC SEL, and I just search for, it comes up a whole bunch of times. I just search for the table that describes the register. So this is register 26-3. So here's the register. Okay. So these are the FNOSC bits. These 3 bits are the ones that set the oscillator speed for the from the FOSC SEL register. And there are 3 bits, so you can have these options with those 3 bits. So for example, if you have these bits as 1, if these bits are 111, then that will set up an 8 megahertz oscillator with a divide by n postscaler where you choose the n value. So you can see setting those bits to 110 gives you 500 kilohertz oscillator, and so on and so forth. So this line of code will set those bits in that register for you. So all you have to do is set that line of code, choose the correct option. At the end of this lecture, there's a table that shows you all the different options, and that will set those bits for you. So if you choose for example, the LPRC option, that will give you 31 kilohertz oscillator. So let's look at an example. So let's say we want to make an LED on pin 14 blink with a period of 2 seconds and a duty cycle of 50%. So if we have our LED here turning on and off, on pin 14, to turn that LED on and off, we're going to want pin 14 to go from 0 volts to 3.3 volts, where this distance here, so this time distance is 2 seconds, and with 50% duty cycle, that means this time where the voltage is at 3.3 volts is 50% of 2 seconds, or in other words, 1 second. So every second we want the LED to turn on, and then the next second we want the LED to turn off. Okay, and we are going to use a 31 kilohertz LPRC oscillator. So we're going to, basically the goal is to set up, we'll do our pragma config to LPRC. That will give us 31 kilohertz oscillator speed, and we need to write some code so that the light turns on and off every second. Okay, so let's just do a little math. So our oscillator frequency is 31 kilohertz. That means that our clock frequency is 31 kilohertz divided by 2, so that gives us 15.5 kilohertz, which gives us a clock period of 6.45 times 10 to the negative 5th seconds. Okay, so we have the, we can execute one instruction every 6.45 times 10 to the negative seconds. That's one assembly instruction. So we need, basically we need to execute 15,500 instructions to pass away 1 second worth of time. Okay, so how many instructions does a while loop take? So the delay, our delay function in our while loop needs to take, so if it takes 7 instructions to get through that delay function one time, okay, or sorry, to get through that while loop one time, if that took 7 instructions, then we need to go through that while loop 2,214 times to pass 1 second's worth of time. So where does this 7 instructions come from? So to figure that out, we go over to our delay function. Okay, so here's a delay function, and we need to figure out how many, or what to pass in for our integer s, so that this thing can count sufficiently long enough to pass 1 second's worth of time. Okay, so to figure out how many assembly instructions, and in other words, clock cycles, will be taken up by each time through this while loop that's just there to waste time or to pass time, we need to go into debug mode, set a breakpoint, run the program, stop at the breakpoint, and then hit the window button, go to debugger, and then click on disassembly. Okay, and then we can look at how many assembly instructions there are for that while loop. So we've got 1, 2, 3, 4, 5, 6, and 7 lines of assembly code. So every time it goes through that while loop, it's going to burn up 7 clock cycles because there's one assembly line for every clock cycle. Okay, so let's go back here. So if we need 15,500 clock cycles to pass 1 second's worth of time, and each time through the while loop chews up 7 clock cycles, then we need to go through that while loop 2,214 times. Okay, and so here's what we just looked at, the assembly code from the MPLAB IDE. I've just copied and pasted it there. All right, so let's talk about oscillator postscaling. So an oscillator postscaler is a circuit that divides the frequency of the oscillator output by some predetermined factor to generate a lower frequency clock signal. So this is basically a way of slowing down the oscillator in runtime. So so you can set the original oscillator speed at compile time. That can't change, but you can post scale it to slow it down by some factor in runtime. So for example, our PIC provides an 8 megahertz oscillator with post scaling, or we can choose a low power oscillator, which is the 500 kilohertz oscillator with post scaling. These are the post scaling values you can choose. So you can slow down your oscillator by a factor of 1, 2, 4, all the way out to a factor of 256. Okay, and it basically divides the rate of the selected. It divides by the selected post scaling value. So it divides the oscillator rate by the selected post scaling value. So this is done using the RC div bits of the clock div register. So let's search for the clock div register in our data sheet. It's right here. So if you were to look for that yourself, you do search for clock div, and that pulls up all these results, and then you can just kind of click through these and see which one pulls up the actual register information. So here's our clock div register, and it has these what are called RC div bits. So those are 3 bits, RC div 0, 1, and 2. And you set these bits you can set these bits to give you the post scaler you want. So for example, we've got 2 options. We've got the 8 megahertz oscillator with post scaler, and we've got the 500 kilohertz oscillator with post scaler. Yeah. So if we set the RC div bits to 0, it will give us the full 500 kilohertz because it's a divide by 1 post scaler. So it'll give us the full 500 kilohertz oscillator if we're choosing the low power one, and it'll give us the full 8 megahertz oscillator if we're choosing the high power one divide by 1. Okay. Alrighty. So let's look at an example. Erase this. Okay. So how long will each instruction take if we have the following configuration? So let's say we use the pre-pragma or the hashtag pragma configuration for our clock as LPFRC. So that's the low power fast resistor capacitor. So that's the 500 kilohertz oscillator. And we're going to set the RC div bits to 101. So you'll notice these bits here, okay, can be set using this definition. So underscore RC div equals, you set that equal to a number, that will directly set these 3 bits here in runtime. Okay, so for the 500 kilohertz oscillator, and we're going to set RC div to 101. We go down here. Here's our 500. Here's the 500 kilohertz option. 101. That's a divide by 32 postscaler. So that's going to slow down our clock speed, or sorry, our oscillator speed by a factor of 32. So we go 500 kilohertz divided by 32. That gives us 15.62 kilohertz. Okay. Okay, so this is, yeah, so that's what we just did here. So our oscillator speed divided by 500 kilohertz divided by 32, that gives us 15.625 kilohertz. And then our clock speed is always half of the oscillator speed. So our clock speed is half of 15.625 kilohertz, so our clock speed is 7.81 kilohertz. And then if we look, remember our original question was how long will each instruction take? So if we are doing 7,810 instructions per second, that's what this says, then for each of those instructions it takes 128 microseconds, right? So it's just the period of our clock frequency. Okay, so just to summarize, assembly instructions are always executed at half the oscillator speed, regardless of any post-scaling selection. The post-scaler value changes the oscillator speed. So for example, if we're using an 8 megahertz FRC div oscillator with a divide by 2 post-scaler, that's going to give us an oscillator speed of 4 megahertz and then a clock speed of 2 megahertz, which is half the oscillator. I keep saying speed, but I meant frequency. Gives us a clock frequency of 2 megahertz, which is half the oscillator frequency. The default is, and this is super important, so that you get your timing correct, the default is 8 megahertz FRC divided by 2 postscalers. So in other words, in your code, if you don't include anything here, you will get an 8 megahertz oscillator divided by 2 postscalers, so that drops it to 4 megahertz oscillator, which gives you 2 megahertz clock frequency. So you'll execute 2 million instructions per second if you don't include anything, okay? Also, well, let me, yeah, so how do you choose 8 megahertz? Actually, I'll get to that in a second. Let's just finish the summary. So the oscillator is chosen at compile time. Okay, so this line of code gets compiled, you upload it to your PIC, it sets up the PIC for a specific oscillator and it cannot change. Okay, but the postscalers can be chosen at runtime. So you can set those underscore RC div values. Did I do that right? RC div, yeah. Yep, so it highlights it in blue. That means you know you have a correct definition here. So if I put RC, let's see, dig, should turn black because there's no definition. Okay, so blue means there's a definition for that one. So RC div, go to the data sheet, RC div, let's say a divide by 1, 0, 0, 0, come back here, 0, 0, 0, so that's a divide by 1, this is a divide by 1 postscaler. Okay. Okay. Let's go back here. Okay, so oscillator chosen at compile time, postscalers chosen at runtime. So this, you can, anywhere in your main loop, you can reset the postscaler if you want to if you want to use different oscillator speed at some point. Okay, this table is really handy. So this column here gives you the definitions that can be used for your oscillator speed at compile time. So if we used, for example, FRC, that would give us an 8 megahertz oscillator with 4 megahertz clock speed, and FRC has no post-scaling option. So if you set FRC, you cannot post-scale. Okay, it's just going to give you the fastest execution time possible. But let's say we wanted to use a postscaler and slow things way down. So we could use, for example, LPFRC for the compile time, LPFRC, so that's our clock speed. And then we could do a divide by 4 postscaler. So that would be an RC div value of 0B010. So down here we could say RC div 0B010. And that would give us a postscaler divided by 4 postscaler. Oh, incidentally, I made a mistake here. So back to this line of code. So that was, I said this was a divide by 1 postscaler. Okay, this is not binary here. I should explicitly say 0B. That said, that 0B000 should be the same as 000. Let's see if this compiles. I'm just curious. So let's stop running. Let's see if this compiles. Yeah, so the compiler, yeah, just be careful. Oops. Press demo. Is this our, that's our blink LED. Make sure I'm in the right file, yeah. Yeah, okay. So this is decimal 0. So that's the same as that. So just be careful, unlike me. All right, so our divide by 1 postscaler. So that was, yeah, 000. Okay. Okay, so this table's handy. It tells you what to use for your RC div value given the oscillator you have chosen, and then it tells you exactly your oscillator frequency as well as your clock frequency. So this will be handy for the labs. All right, that's it, folks. Thank you.